In Lesson 1.3, Evaluating Limits Analytically, we'll see how to use your already gathered algebra and precalculus knowledge in order to find limits without having to use numerical tables or graphs or anything complicated like that. We'll simply use the knowledge you already have to somehow simplify or break down a function so that we can find its limit through a method of direct substitution, which fortunately we already talked about in the last lesson. If you recall, direct substitution is simply where you take the value that x is tending to, plug it into the function, and see what you get for y. Of course, as we saw in lesson 1.2, sometimes it works and it's beautiful. Unfortunately, sometimes it doesn't work and we need to take other approaches. We've already learned how to use tables. We've already learned how to use graphs. And in this lesson, again, we'll learn how to reuse our algebra to accomplish these goals. However, before progressing into any of the examples, let's first talk about some basic limits and set the stage for what's to come. To evaluate these basic limits, we are going to use that direct substitution method. So if we take a look at this, we're going to consider b and c to be real numbers. And all we're going to do with these 5 limits is try to find the limit as x approaches c, well, for the first 3 anyhow. So, what is the limit of a constant function b as the x value approaches c? Well, if this is a constant function, it's not going to change at all no matter where we go. And so the limit of this is simply going to be that constant value. Easy enough. Consider this one, the limit of x as x approaches c. Here we can do the direct substitution. In fact, if you think about it graphically, if we graph y equals x, we're going to get this 45-degree line here. And of course, anywhere we go on it in the x is going to yield that same value in the y. If that seems a little complicated, don't worry about it. We're just doing a direct substitution. And so the limit of x as x approaches c is simply c. And here we go again, a short polynomial function. Nothing special about it, no rational part, nothing crazy here. The limit of x to the nth power as x approaches c, well, direct substitute that, and you'll get that that is simply c to the nth power. Now, these other 2 basic limits involve trigonometry, but don't let that scare you. This first one we've actually already seen, and hopefully you can even extend that to sine of kx over x. Of course, for what's given here, this is simply going to equal 1. But as we saw in the last lesson, if we do the limit as x approaches 0 of sine kx over x, that's just going to give us k. Perhaps this one is a little bit more important to remember. This is simply a consequence. So there you go. This last one we're not going to delve too deep into. I certainly welcome you to graph it, and there's a lot of ways that we can prove what I'm about to show you later in this course. But for right now, I'll tell you that the limit of this function as x approaches 0 is simply going to be 0. And so those are some of our basic limits. We're going to use those as we progress throughout these notes in lesson 1.3. So let's go ahead and begin with example A. Here in example A, we're going to run into what's going to end up being a very, very common type of exercise for you to work out. I always want you to start limits by direct substitution. Always give it a shot. Generally, it's not going to work or else it wouldn't be very interesting. But give it a shot anyway, because you never know. In this situation, we're doing the limit of this function as x approaches negative 3. So if we direct substitute that negative 3, what we'll end up with on top is negative 3 plus 3. And on bottom, we'll have negative 3 squared minus 9. Now, it doesn't take too much math to figure out. That's going to give us 0 over 0, which tells us very little. However, anytime you direct substitute, if you do get 0 over 0, that generally signifies that there is a type of discontinuity at this function, at this location of x. In fact, usually it's just a hole. Hopefully you remember this from pre-calculus. And if that's the case, what we can do is try to simplify the function somehow or another. Hopefully you recognize that the denominator of this function can actually be factored into x plus 3 times the quantity x minus 3. Now, who cares? What's the point? Something very important is going to happen here. Of course, we're going to have 2 factors. They're going to cancel each other out. And that's going to leave us with the limit as x approaches negative 3 of the very simple rational function 1 over x minus 3. Now if we direct substitute, I think you're going to find something very, very special. And what is that? That's simply going to be 1 over negative 6. That is a real number. All right? That is the limit of this function. And in fact, if you were to graph this function, I certainly welcome you to do that, you'll find that there is a hole, or rather a removable discontinuity at x equals negative 3. However, remember what we said in lesson 1.2. We're not interested in what happens at that point, but rather what happens around that point. And if you look at the graph of this, you'll see that what happens around this point is that from both sides, we're converging to y equals negative 1/6. That's why that is the limit. Just a little side note here. Anytime you have a function, if you want to create a hole in that function, all you need to do is multiply the numerator and denominator by a common term, and that'll end up giving you a function that doesn't exist at that point, but does have a limit there. So lots of fun can be had with that. Anyway, all that being done, let's take a look at example B. In example B, we're going to find out if you're following directions. Go ahead and pause this video for just a moment and try to work out this problem on your own. It's not a very difficult problem. You should have no issues with it. So pause and give it a shot. All right, well, welcome back. Hopefully you actually did try this out. And if you did, I'm assuming that you probably went ahead and tried to factor this thing, which was no difficult task. This would be the limit as x approaches 0. And if we factor this nasty rational function right here, we're going to get the quantity x minus 4 multiplied by the quantity x minus 1 for our numerator. And down on the denominator, you're going to have an x minus 4 times a quantity x plus 2. You probably looked at that and said, oh, well, that's fantastic. I can cancel out a common factor, run the 0 through both of these, and find out that my answer is negative 1/2. And if that's what you did, you got it right. Congratulations. I told you it was easy. However, had you followed my directions from earlier when I said you should always try direct substitution first, look what you could have done. Rather than factoring at all, if I just take x equals 0 and plug it into all of my x's, 2 of them on top, 2 of them on bottom, well, all of those are gone. And look what I'm left with here, 4 over negative 8. And of course, if you reduce that, this problem didn't need to be factored at all. Always try direct substitution first. Could save you a lot of time later on, so don't forget that little tidbit. All right, well, let's go ahead and move on to example C, where we will try direct substitution again and see what happens with that. Hopefully, if you were one of the people that I caught not direct substituting on the last example, hopefully that's what you're going to try first on this example. Go ahead, give it a shot. We're looking for the limit of this nasty function as x approaches 0. Go ahead, try your direct substitution. What happens? I'll give you a second here. All right, do you end up with, let's see, 1/3? If you end up with 1/3, great. That's correct. Excellent. Way to go. You might have gotten negative 1 over negative 3, but it all reduces to positive. All right, so not very interesting. However, with this example, I'm going to pose this question. This function that you're looking at here, where does it have a discontinuity? What kind of discontinuity does it have at that place? And what is the limit of this function as we approach that discontinuity? Well, let's answer those questions one by one. Let's start with, does this have a discontinuity, and where is it? If you look at this, clearly the denominator will equal 0 when x is 3. So let's see what happens when x equals 3. Let's see here. We'll get on top 0, and on bottom we'll get 0. So there is a discontinuity there. Because it's 0 over 0, that tells us that it is a removable discontinuity. In other words, it has a hole at x equals 3. So let's go ahead and answer the third question. What is the limit of this function as x approaches 3? We're essentially doing the same problem that we just did all over again, the one you did here, and we're going to try direct substitution But you already know what's going to happen because we've already done that. You're going to get 0 over 0, and that's no good. So we need to play with this a little bit. Can we factor this function? And the answer to that is, unfortunately, no, we can't. But you've been through Algebra 2, you've been through pre-calculus, you know what to do with this. Let's go ahead and multiply this by the conjugate of the numerator. Essentially, we are going to rationalize the numerator. We're used to doing this with the denominator, but you never know when it's called for on top as well as on bottom. So if we go ahead and multiply by the conjugate of the numerator, which looks like this, all we need to do is a little bit of multiplication and a little bit of simplification. I'll leave that as an exercise to you. That should only take you a few seconds. But I'm going to go ahead and write the result down here. What we should end up with is actually going to be x minus 3 in the numerator. And in the denominator, we'll have x minus 3 times the factor x square root of x plus 1 plus 2. Hopefully you got that on your own. I promise you it is correct. So if you didn't get that, go back and check again. Anyhow, taking a look at this, it's clear what's going to happen. We have a common factor. And now, if we direct substitute our x in, let's see what's going to happen. That's going to give us, well, on top, once we cancel those factors, we just have a 1 on top. So that's easy enough. And when we plug 3 into the bottom, well, it looks like we're going to get a 4 overall. So this function does have a discontinuity at x equals 3. It is a removable discontinuity, or a hole, but the limit of this function does exist at x equals 3, and it is 1/4. Take a look at the graph if you want to prove it to yourself, and you'll see that it is the case. So with that, let's take a look at a little more difficult of an example with example D. Problems involving complex fractions tend to be very troublesome for a lot of students. But remember, the basic idea here is to turn your complex fraction into a normal, regular, happy, everyday fraction, somehow or another. Now, in this particular problem, there's a lot of ways we could do that. This nasty function here, we could turn into, well, let's see. We could say this is our numerator, 1 over x plus 4 minus 1/4, and we could multiply that by the reciprocal of the denominator. And if we do that, what we'll end up with is something along the lines of this. And what we can do now is try to get common denominators, put it all together, see how it works. You could go that route. My advice is actually going to be to try to find a common denominator from the get-go. In other words, to simplify the numerator portion of this complex fraction and then simplify from there. Let's see what that would look like and how I could go about doing that. Well, if I want to find a common denominator of these two fractions, clearly there needs to be a factor of 4 in this fraction, which I'll do by multiplying the whole thing by 4 on the top and bottom. And to get a common denominator on this other fraction, I simply need to have an x plus 4 and a 4 on the bottom. So the denominators will look the same. How did I get the denominator to look like that? Well, I multiplied by the quantity x plus 4. And I'll go ahead and do that on top as well. Just for brevity's sake, go ahead and simplify that and see that you do end up at the original negative 1/4. So everything is still copacetic. Now, unfortunately, this does not look like an easier complex fraction than what I started off with. But if we go ahead and combine these two like-termed or like-denominator fractions together, look what's going to happen. I'm going to have 4 times the quantity x plus 4 in the denominator. But what am I going to have in the numerator? Well, I'll have 4 minus x and minus 4. Wow, that's just going to turn into x. And that's pretty nice, because what I'm going to do now is be able to cancel out that x and that x. You can multiply by the reciprocal of the denominator if you so choose. Any way you want to look at it, these two x's are going to cancel out. And I'm left with the rather easy problem then. The limit is x approaches 0 of what I'll have is 1 over 4 times the quantity x plus 4. So this isn't too bad. Unfortunately, I have lost something here. Maybe you caught it. This should be a negative x that canceled out. So this will be a negative 1. Okay, problem solved. Now, if I go ahead and just direct substitute, because remember, that's what I love to do the most, Plug the 0 in for x. What am I going to end up with here? Simply negative 1/16. And that's a nice, happy answer. Now, the more clever of you might have asked yourself, well, since this negative 1/4 is essentially a what we call a scalar multiple, would it be legitimate for me to have gone from this step here and simply pulled the negative 1/4 out? In other words, could I have said that this is negative 1/4 multiplied by the limit of what's left? You probably didn't think of this, but it is going to lead to something very important here in just a second. So what would have happened had I done that? Well, take a look. This would have been negative 1/4. Direct substitute the 0 for x, and for this I'll get 1/4. And of course, that will bring us right back to negative 1/16. And that is actually going to bring us to the first of our properties of limits. These are very simple, very common sense things that if I didn't tell you, you would probably be able to figure out on your own. However, for formality's sake, let's go ahead and run through them anyway. Here we go with the properties of limits. Before we look at the properties of limits, we need to make sure that we have a few basic assumptions down. We're going to treat b and c as real numbers, and n is a positive integer. Okay, that's pretty standard fare. We do have that the limit of the function f of x as x approaches this real number c equals L, and likewise the limit of the function g of x as x approaches c equals k. Now that doesn't necessarily mean that f of c equals L. Remember, we're only talking about limits, not algebraic evaluations. So let's take a look at our first property here, the scalar multiple. You saw an example of that when we were doing example D, where we pulled that negative 1/4 out, handled the limit, and then just multiplied at the end. If we have something like that, where we have a scalar multiple, which we're going to call b, multiplied by a function, all we really need to do is just pull that b out front. And if we do that, look what we're going to get. We're going to get b times the limit of f of x as x approaches c. Now the good news here, we know what the limit of f of x is as x approaches c. And so all we're really going to end up with here is b multiplied by L. Simple enough. If it's a scalar multiple. Remember, scalar multiple means that it is a constant multiple, a 4 or negative pi or something like that. If it is a variable that's multiplying it, this is not going to apply, and we'll have to use other methods that we'll learn later. Now, let's say we have the sum or difference of two functions, and we're trying to find the limit as x approaches c of that sum or difference. That's very easy, because we can actually split these up and do the limit of f of x plus or minus the limit of g of x. And of course, that's simply going to give us L plus or minus k. So that's easy enough. Likewise, the product. If we're doing the product of some function times the product of another function, all we need to do is simply multiply their limits to find the composite limit. Easy enough. If it's a rational function like this, f of x over g of x, we can evaluate that, and that will simply be L over k, usually. When would this not work? When would the limit of this not equal the limit of their quotient? Well, that's provided that k is not equal to 0. K equals 0, we have a whole other thing going on, and we're not going to deal with that here. And the last one we need to look at is the power. This is easy enough. We're just going to direct substitute again, essentially, and end up with L to the n power. So there's your properties of limits. They're very easy. As I said earlier, you probably could have figured them out yourself, but now we're all on the same page as we move on to example E. Don't get scared. Example E does involve trig functions, but they're not difficult, they're not going to be troublesome to deal with, nothing like that. However, before we begin anything else on this problem, I do want you to try one thing, and you should know what that is. Go ahead and direct substitute. See how it all works out for you. I'll do it with you here. If we're doing the limit as theta approaches 0, this numerator, cosine of 0, well, that's going to give us 1, so that's nice and happy. But the tangent of 0 is going to give us 0. And it's pretty evident to see that we're going to have 3 times 0 on bottom, and that's going to give us 0 over 0. That's bad. In the past, previously, in this particular lesson, we've said that that's a sign that we need to factor, cancel things out, there's a hole in the graph, things like that. So go ahead, try factoring this. I bet you won't be able to. However, cosine theta multiplied by tangent theta, that's going to equal something really nice. In fact, let me go ahead and write that out here. Cosine theta multiplied by tangent theta. Oh yeah, that's right. Tangent theta can be written like that. And if we do that, watch what's going to happen. The cosines cancel out. And look what we have left in our numerator. It's just going to be sine theta. So let me go ahead and rewrite this problem. We'll do the limit as theta approaches 0 of sine theta over the quantity 3 theta. That looks a lot nicer. It is a lot nicer. In fact, it looks very, very familiar. Look at the top of your notes where we have some basic limits. Does this one look familiar? You might say, well, close, but not exactly. And then what I'll say is we can make it look more like what we see above. In fact, watch this. I'm going to pull 1/3 away from this function. And look what that will do for us. Aha! This part looks very familiar. And this part, the 1/3, that's a scalar multiple. So what I'm actually working with here is 1/3 times the limit as theta approaches 0 of sine theta over theta. Well, that's pretty beautiful because here goes my 1/3. And we know that this, from up above, we know that that equals 1. So what do we end up with for the limit of all this stuff? It's simply going to be 1/3. And that's how we use these properties of limits to simplify problems down to a more manageable state. Easily done. Let's take a look at one more example, and then I have to tell you a little bit about my favorite theorem to date. So now that we've learned some methods for evaluating limits analytically, we've learned factoring, we've rationalized, we have combined fractions, finding like denominators, we've used these basic limits, we've done all this stuff this lesson. So let's culminate it in example F. Go ahead and try this on your own before I work it out. It is trig, it does have a couple cosine thetas, and it does have an absolute value, so maybe that's going to make it kind of nasty also. But go ahead and try it and see how it works out for you. Did you factor? You weren't able to. Rationalizing? There's no square roots here. None of that stuff. Combining fractions? No. In fact, this is back to the basics. If we direct substitute 0 in for theta, we'll have cosine of 0 on top, and we will have the absolute value of cosine 0 on bottom. What is that going to give us? Well, cosine of 0 is simply 1. The absolute value of cosine 0 is also just 1. And so this is actually a very easy limit to have done using direct substitution. Go ahead and try graphing this. See what the graph looks like. It's very interesting. It's steps of sorts, maybe. You'll see when you look at it. But clearly, when theta approaches 0, the function approaches 1. Easy enough. So, that being said, let's go ahead and take a look at the squeeze theorem, which I'm not quite sure why it's in this lesson, but it's pretty easy, pretty exciting. Let's take a look at it now. So let's talk about the squeeze theorem. This is a very fun and very exciting theorem. It actually is pretty interesting, and the squeeze theorem is a very appropriate name for it. Essentially, we're going to have 3 functions, and 2 of those functions are going to squeeze the third function together. Well, this is a terrible story without illustrations, so let me show you exactly what I'm talking about. Here we have a function that I'm going to call g. Very exciting. I'm also going to have another function, and I'm going to call this function h. So I have 2 functions, and I'm going to tell you that on an open interval that contains the x value c, on this interval right here, I'm going to tell you that g of x is always greater or equal to h of x. So never will g drop below h on this particular open interval. I'm going to tell you one other very interesting fact. The limit as x approaches c of g of x, we're going to say is L. Furthermore, we're going to say the limit as x approaches c of h of x also equals L. So in other words, their limits are the same as x approaches c. Now, here we go. This is the climax. We have a third function. And the third function, which I'm going to define as f, is always going to be less than g, but is always going to be greater than h on this open interval containing c. In other words, it's always going to be between g and h, as you can see here. Now the question is, what is the limit as x approaches c of f of x? Take a look at the picture. Take a look at the picture. The limit as we approach this dashed line of the top function is L. The limit as x approaches this dashed line of the bottom function is L. And the third function, f, is always caught in between those two. Clearly, the limit of f of x will need to be L also. The blue functions on top and bottom are essentially squeezing f of x. And if they're equal at some point, then f of x will have to be equal at that point as well. So let's go ahead and formalize this because it's really hard to tell a math story when you're taking the AP exam. So let's put it like this. Let's say if we have a function h of x, which is always less than or equal to f of x, which itself is always less than or equal to g of x. And again, this is on some open interval. And that open interval must contain c. And that is an x value, c. So if that's the case, on some open interval containing c, and furthermore, if the limit as x approaches c of h of x equals the limit as x approaches c of g of x, and let's just define that limit as L, then our conclusion must be, as we said in our story picture over here, then we must say that the limit as x approaches c of the function that is squeezed between those two must also equal L. It's not mind-blowing by any means. You can find examples of this everywhere. Ask me for examples and you'll get some. But it is an important theorem that will become more and more relevant later on. And even if it's not relevant, it sure is fun and exciting. So, remembering all these things that we talked about, limits, how to evaluate them analytically by factoring and canceling, by rationalizing, by combining fractions, by direct substitution, using some basic limits and properties of limits and all these good things. Remember all this as you continue with your homework, and good luck.